Here we go, 18. I'm going to take this figure, and here's the big part. I don't know if anybody caught this as you were reading, but you are going to continuously rotate it around AB, not AC. All right, make sure you rotate it around AB. So as I continuously rotate it, what's this 3D object going to be formed? That's going to be a cone, right? And it wants me to find the volume of that cone. Where can I find that formula? Because you don't need to memorize it. Reference table, 1/3 pi r squared times the height. All right, if I am revolving it around AB, what is AC acting as right now then? Ooh, that would be the height if I go around CA. That's the radius of the bottom circle on the cone. That's the radius is 4. So 1/3 pi 4 squared. And then what would have been the height if I rotated around AB? 6. Yes, it would be 6. So we end up with 1/3 pi 16 times 6, which I believe ended up being 32 pi. All right, 32 pi. So where you rotated it around ended up being the height, because it kind of looks like this at the end. All right, here's your side of 6, and here's your 4 right here. Okay. Will, hello. What do we got for 27? Oh. And this is the same exam the kids took last year. So this is where every time I told you that story about Cavallari's principle coming up, this was the problem. When did we ever do this? Oh, we did. Explain why the volumes are equal. All right, but they didn't want, if you, like a lot of kids found the volumes and that wasn't good enough. You had to explain using Cavallari's principle. Cavallari's principle says two things. If they have the same heights, do they have the same heights? Yeah. The prisms. Yeah, they do. What are the prism heights? 14 and 14. The height of a prism is the distance between the two bases. So they both have a height of 14. So let me just get out what I ended up writing. Yep. So both prisms have the same height. And, which would have been 14. Okay, what shape is the cross-sectional area in here? It's a triangle. Do both triangles have the same area? Yes, they do. Why? And cross-sectional areas. How would you find the area of that cross-section right there? What would be the formula to find the area of that cross-section? 1/2 5 times 8, 8 times 5, which makes the volumes the same. That's the two things you got to test out. The heights are the same, cross-sectional areas are the same. Makes the volumes equal. All right, heights are the same, cross-sectional areas are the same. All right. Anything else here? Going. Justin, hello.
For this one, why can't you just say the base area instead of cross-sectional area?
You could do that too. That's fine. Yep, that's fine. Because that's what the cross-sectional area is going to be, is whatever the base was.
Okay.
Yep. Next, Amy. 26, everybody. Area of a sector, all right, that's a formula I need to know. Not on the reference sheet. There are two formulas for a sector, one in radians, one in degrees. What is given to me here? Degrees, correct? Okay, I don't want to come out and give it to you. I want to make sure you know where to find it in case you're studying on your own in the next couple weeks. Go ahead, go to your cold hard facts packet that you have. You guys have a page of circle stuff, and then on the following page is area of a sector, both in radians and in degrees. Make sure it's area of a sector you're looking at. Don't look at the one next to it, which says sector length. So anybody want to just, in degrees, what's the area of a sector formula? Measure over 360 times pi r squared. When we say measure, that's the angle measure in degrees. In this case, 40 over 360 times pi, radius, 4.5 squared. Now it does say leave in terms of pi. So now that I have my calculator out, here's all I'm going to do. Fraction template. I'm going to go 40 over 360. And then I will multiply that by 4.5 squared, leaving out the pi. So 2.25 pi. Another acceptable answer. I don't know if anybody left it as a fraction, but you could also do 9 pi over 4 if you wanted as well. Okay. Both answers acceptable. Anything else here? Because I am going to go back to that proof. Yep. Just as long as the pi is not with the 4. That does make a difference. What's that? Sure. Why? Here we go. Because remember, this pi is really over 1. So it goes with the numerators, right? Okay. Anything else? Okay. Leave this right off to the side, this June exam. I need you to go back to the August. This one was in the August one, correct? The one we didn't finish yesterday at the end of class, the circle one. Okay, just that's the last question I'm going to do from there, and then we'll put it to rest. We talked about how we were going to prove the triangle similar, but we did not actually write down everything, which is probably the most important part of this proof. So let me just review what we did yesterday. These were parallel. So we said these angles were congruent for some certain reason. And I believe other people said this was a right angle and this was a right angle. Okay, because we needed to prove the triangle similar by angle. Okay, let's actually write down everything we need here because there's a lot of important stuff in here that involves circles. I did mention yesterday, you will get a point off if you clearly don't write out all your givens. If you put like an arrow down or you're squiggly with a big G that says given there, that's not going to cut it. All right, and then I definitely didn't practice what I preached because I want to get through as many review questions as I can. All right, I don't know. Anybody want to take claim to who told me those angles were congruent yesterday at the end of class? Heaven did. You told me those. Okay. Heaven told me that angle at the end of class, angle BCA, was congruent to angle CAD, CAE, either one. Somebody other than her, why is that a true statement? Well, what do I have first? Parallel lines imply alternate interior angles congruent. Okay. Now let's take care of the right angles. Let's start with angle ABC. Anybody tell me why ABC is a right angle? Because it's a different reason than why that's a right angle. And I know this was not the greatest of units for us, but we're going to get through it. ABC is a right angle. Anybody just looking at the diagram can tell me why here. Got to get specific, Emily. Okay, hold on right there. Sorry to cut you off. You have to tell me it's what type of angle? Inscribed angles. Inscribed angles. Continue, Emily. Sorry. Okay, keep going because because I'm saying it's a right angle. So how do I know it's exactly 90 degrees? So inscribed angles drawn to, in this case, what type of arc is AC? I want to get specific here. How do you know that? Inscribed angles drawn to a semicircle. Anybody remember what else you could have instead of semicircle that's appropriate? Diameter. Nice job, Justin. Inscribed angles drawn to a semicircle are right angles. Yes. Gotta write inscribed, though. I see too many times angles, chords drawn to a diameter. No, inscribed angles drawn to a diameter. Woo! All right, let's go. Here's the big one. Why is that bad boy a right angle? Oh, woo! Come on. Will, you think you got it? You're there. I don't want you to say the word drawn to a tangent, though. It's drawn to a point of tangency. But whoa, before you guys start writing down like crazy, that theorem that came from Will does not say it's a right angle. It says, what about the two lines? They're perpendicular. So that's what yeah. God, I hate this class. That's what I have to write down first. All right? Because I could feel the pressure already coming. Somebody's going to correct me. AC, perpendicular to CE. By the way, quick update. I did have a tear come out of my eye yesterday. My contact just was scratching the life out of my eye, and then all of a sudden this piece of little droplet of water came out. So I didn't know what was going on. But it was all good because then I kind of just like cut myself a little on my arm and some oil leaked out. So there wasn't any blood. So we were good. We were good. The machine is still alive. All right, we were good. There was no blood. All right, so here's the actual theorem. Will, you said a diameter. You could also certainly write a radius. So a diameter drawn to, yes, not to a tangent, drawn to the point of tangency. Is perpendicular to the tangent. This theorem only says perpendicular lines exist, not a right angle. But now that you have perpendicular lines, what do you have now? Now you got the right angle. So angle, what's that angle name there? ACE is a right angle. And that's an old school one, way back, maybe like October, November. Why is it a right angle? Okay, you guys keep going now. I don't want to say anything. What should be next here? They're congruent. Yes, tell me those two are congruent now. So angle ABC is congruent to ACE. All right angles are congruent. Okay, do you have two pairs of congruent angles? What do you know about the two triangles? Similar, good. Nobody said congruent. Nice job. Triangle ABC. Similar to, let's see, if I go ABC. What is it? ECA, okay. By angle. And then let's finish this off right by saying the sides are in the same ratio. BC over CA is equal to, what do you got there? AB over EC. A little reason. You guys know I'm going to try to prepare you for any scenario. What would be the next step if I had to write a next step? BC times EC equals CA times AB because product of the means equals product of the extremes. Yes. All right, good. All set? All right, there you go. You can put that August one away, and let's get the June one back out. Anybody want to throw a prediction out, score for them? Anybody want to throw a score prediction for themselves out? 99. Oh, wow. Okay, you got it, Sean. Wow, here we go. 12. Here we go, 12. 99. Whew. No multiple choice wrong then, huh? 12. I just want to see if you can do these on your own now. 12. Good feeling it'll be on there, even though I have no idea what's on there. I would be confident in predicting that one of these would be on there, either a multiple choice or part 2. What's the center and radius? Now, I don't know if any of you are getting a little concerned because there's nothing to put with the x. That's fine. You just don't complete the square on that one. Just complete the square on the y's. Okay, and leave it x squared. That should tell you right away what's your x coordinate going to be. 0, and then that really doesn't help you given the multiple choices. But yeah, good. The x coordinate of the center is going to be 0, and then y is going to be something else when we complete the square. Just to make sure we're all on the same track, what number is completing the square for the y's? What's that new c value that's completing the square? Bless you. Should be positive 36, everyone. Make sure you add it to the right side as well. What's inside your parentheses? Y minus 6 squared, and then over here you should have 16. Ask now. Center then, we know it's going to be 0 something. 0, 6, change the sign, 0, 6. And then your radius, not 16, but 4, good. All right, just another one of those. 28. 28 now. Hey, fun fact before we start. When volleyballs are purchased, they are not fully inflated. There you go. There's your fun Regents fact for the day. Volleyballs, we're saying they're modeled by a sphere in case people are going to argue that. Partially inflated, their volume's 180 inches cubed. Fully inflated, 294 cubic inches. Tell me to the nearest tenth, how much does the radius increase? How much does the radius increase? Is this a formula I got to remember? Nope, it's on the formula sheet. Go ahead, find it. Volume equals, for a sphere, 4/3 pi r cubed. Yep. So we'll do partially inflated, and then we'll do the fully inflated. All right, so partially was 180, and you're solving for the radius. And fully 294, solving for the radius. Don't round anything to the end. Keep those full decimals rocking. Just so, what's everyone going to try to do first? Because there's multiple steps. I just want to hear what you're trying to do first. Yeah, I always like to take the fraction out. That's just me. Could you divide by pi first? Yeah, that's fine too. I like to get the fraction out of there first, though. And at the end, how are you getting rid of that exponent of 3? Where's that button? Because I cannot help you on the actual day of the test when you're like, hey, can you explain what cube root button is again? I'll just give you a gentle pat on the back and say, good luck, kid, as I walk by. And I don't mean on the test, I mean in life. Okay? All right? Too harsh. Week 39. Where is it located in all seriousness? Math number 4. Yep. So go ahead, find the radius of both, and then I'm interested to see what you're going to do with the 2. Interested to see what you're going to do to the 2 to find the final answer. You guys are finding the radii now. How are you going to find how much the radius increases by? What are you going to do with these 2 radii to find out how much it increases by? And I know some of you are looking at me like, are you kidding me? You're asking me that? Of course I'm going to subtract them, but I try to figure out what's going through your mind all the time. And in the volume unit, we've divided a ton. All right, so I'm just hoping you guys don't divide these and you're going to subtract them to find what the increase is. Okay, so the change, I don't write out full decimals. I just roll like that. All right, sorry. And to the nearest 1/10 of an inch, the change in radii in a partially flated to fully 6. Calm down. 0.6 inches. Yep. It's only 2 points, huh? I would have thought that would have been at least a 3-pointer, but okay. Any questions from you guys? Going? Yeah, more. You need more. Come on. Feed the beast. Let's go. Next one. No, there are. At the very beginning of the parts, if you read through it, it tells you how much each is. 30. How did I make ABCD, ABC go on to EFD? All right, AB, bless you, to DE. So we know those 2 have to match up. We know AC's got to match up with DF. And we know angle A is congruent to angle D, so they have to match up. Write a sequence, meaning more than one set of transformations that would map them onto each other. All right, so you got choices, right? You have, let's see, translation, rotation, reflection, and dilation. Those are your big 4, but we need 2 or more of them that'll get them onto each other. And I'm doing this one with you because it is not good enough just to give me rotation. That's it. We need to get specific about the rotation if you want to do one. We got to get specific about the reflection if you want to do one. So let's just start with the general one right now. Oh, you want to rotate first? Okay, that's fine. So I'll start with rotate triangle ABC, but that will not cut it. You need to tell me rotate it around what point. In this case, You can't tell me degree measure because that's impossible, right? Everyone agree? You can't tell me a degree measure here. But you could tell me what direction you're going to rotate it, clockwise versus counterclockwise. All right, so let's make a decision here. Rotate triangle ABC, and since there is no point or points in here, it's not on a graph, I would pick one of the vertices of the triangle you're rotating. So you want to, okay, fine. Rotate triangle ABC around point C. And again, is point C the only one? No, you could have easily said point B or A. Which direction? Okay, so you want to rotate this point around point C. So point C is going to stay where it is, and this is going to go clockwise. Fine. Clockwise. And again, I can't give a measurement here. There's no way I can give her measurement. Followed by, okay, you guys have rotated it. Great. So I've rotated it clockwise around point C. What am I going to do now to map it onto FED? Okay, followed by a translation. You need a little more than translation, though. How do we usually translate? Anybody remember along a what? Anybody remember? A vector. No, we don't remember that part there. Direction and distance. So if it's going like this, this means I'm gonna slide everything this way, this length. Okay, that's fine. I'm glad we're going over it then. Followed by a translation along. Now, what point did you rotate around? C. That's got to be in your vector then. What point does C match up with? C matches up with F. So we have to, after we rotate it, we're going to translate it along vector CF. Now, how would that have changed if you rotated around point A? Now it would be along vector AD. Slide it along the matching points. Okay? So does this point matter? No, but it does when you find the vector. The vector would matter. Okay? Questions? All right. 31, everybody. 31. Dilation of a line again. Oh, boy. All right. What do you got? What have we already reviewed about lines that get dilated? And they are what to each other? They're parallel to each other. Okay, which means what about their slopes? They stay the same. Okay, so I know that whatever the slope of this line, 3x plus 4y equals 20 is, that'll be the slope of my new line. But I still need to find the y-intercept. All right, 2 scenarios right now for you. 2 scenarios. Ready? I dilated around the origin. I know that's not the case here, but let's just pretend I dilated around the origin. My scale factor is still 1/3. How do I find the new y-intercept? Multiply the old y-intercept by 1/3. If it was centered around the origin. That's how, keep the slope the same, multiply the old y-intercept by 1/3. But is this around the origin? No. And it's probably this second and final case. The point is on the line. Is there any way I can check if 4,2 is on that line? Even easy. I don't want to waste the time graphing. You could if you wanted to down there. Plug it in. Ready? 3 times what's your x-coordinate? 4 plus 4 times 2. Is that equal to 20? Because if it is, it's on the line. Yep. So if the point is on the line, if the center of dilation is on the line, Anybody remember what my new line is? It's the same line. Okay, if the point of dilation is on the original line, the line does not change. Here's why. I have no idea what this line's going to look like, but here you go. Here's 4-2. Ready? It's on the line. We all agree. We just found out it's on the line. Here's a point on the line. If this is 1/3, is this point going to get closer or further away to 4-2? Closer. And guess where it's going to still end up? It's still on the line. This point right here, it's going to get closer, right? But it's still going to be on the line. Every point I dilate is going to end up back on the same line. So that's why our final answer is 3x plus, is it plus? Plus 4y equals 20 is the line because 4-2 is on the original line. Let me go over those scenarios one more time. If it's on the origin, if it's centered around the origin, you take your scale factor and do what with it? Multiply your y-intercept by the scale factor. If the point we're centered around is on the line, the image is the same line. Okay? It's the same line if that point's on the line. And that's, don't bypass that. This seems to be coming up more and more every year. All right, this is like the new thing they want to put on, whether it be in multiple choice or in free response like they did here. All right, I think I got one more to get through here. Oh yeah, the gas station. A gas station, a cylindrical fueling, so we got a cylinder. Holds gasoline, yep. Tank holds a maximum of 20,000 gallons and has a length. Yep, okay. A metal pole is used, yep. How long does the pole need to be in order to reach the bottom of the tank and extend 1 foot outside? Okay. And they give us a little conversion here for a reason. 1 cubic foot equals 7.48 gallons. Does anybody give me another name for what the pole, the portion of the pole inside represents? Diameter? Yeah. So you're telling me if I could find the diameter of the cylinder and do what at the end? Add 1 to it, I'd have the length of the pole. Okay. Where am I going to get that diameter from? Cubic feet, volume of a cylinder. What's the volume of a cylinder from your reference sheet? Pi r squared times height. There's one more small piece we have to worry about. How do you calculate the volume here? What's that? But whoa. I can't plug in 20,000. That's in gallons, and that's going to be in feet. I can't plug in 20,000 here, but hey, that's why they gave us this. 1 cubic foot equals 7.48 gallons. And cubic feet's in volume. So what are you going to do with your 7.48 and the 20,000? Divide it, yep. 20,000 divided by 7.48 will give you how many cubic feet or volume is in this tank. And that'll end up being a number I'm not going to round, right? 2,673.79679 equals pi r squared. What's the height? 34.5. So you guys are going to solve for the radius and then do what to it at the end? Oh, You're going to solve for the radius, multiply it by 2, and then add 1 to it for the pole. Go right ahead, guys. Go right ahead. Make sure you take the square root at the end to find the radius. Just so you know you're on the right track, you should solve for the radius and get about 4.9668 and change. That's why you know you're on the right track. Double it, add 1 to it, pole length, and you guys keep grinding here to the nearest 1/10 of a foot. 10.9 feet. First review session tomorrow after school. There will be late buses.